Welcome to our last Q&A for Organic 1. Okay, so today we've had questions about grades and calculating the grades because tomorrow we have exam 3, which is worth 200 points. And we've had questions about, will there be SN1 and SN2 reactions on exam 3? And then some people have had some questions about retro-synthetic reactions, so I'm going to work one of those. And then we've had questions on how to organize and think about all these reactions that we need to know. Okay, so those are the questions I'm going to hit in this Q&A, and hopefully after you listen to this Q&A you'll feel a little bit more confident. We also have posted an exam wrapper, and that's worth 5 bonus points. Several people have already worked that and timed that, and then they put their reflective thoughts about this material in the course, and then they get 5 bonus points. They just send that to me by email. It also is a good way for you to go through the exam and see for multiple choice how to think about these problems, because the key is also posted, and that was an old exam. Okay, so let's talk about grades. So the way the grades are, you can take whatever your total points are, so you can add your total points in Blackboard. And if you go ahead and you've already submitted quiz 6 for this week, if you go ahead and submit POGL 6, you make sure all your assignments are in. Look at your sapling. Okay, I've already looked at people's sapling. Tonight's the last assignment, so tomorrow I will put in sapling grades into Blackboard. But if you have greater than 75%, then you get all 100 points for your sapling homework. So if you have like maybe a 67%, make sure you get that up to 75. Okay, so don't leave those points on the table. That's 100 points. Your POGL 6 is worth 25 points, and you already have your quiz 6. So you can take whatever your total points are, and then if you want an A, you need to have 900 out of the 1,000 points total. If you want a B, you need to have 800 out of the 1,000 points, because that's 80%. So what you can do is then you can take your total, and basically you take 200 points minus your total points, and that tells you what you need to score on your final, which is exam 3. Now, because we were online and organic chemistry is new, I did not make this a cumulative final. So exam 3 is over chapters 7 through 9. Now that is still semi-cumulative. Okay, so it's still semi-cumulative, meaning I will show you kind of the SN1, SN2 reactions that you're going to see is to make elimination E1. So if you take this compound here and you react it with sulfuric acid and heat, okay, I guess that's not an SN1, that's an E1. Okay, so you get, OH is a horrible leaving group. You have to protonate it to make water. And so this mechanism you would need to know. That leaves, and then you get a carbocation. You know that this is not your more stable carbocation, so you got to do your hydride shift. And then when you do that hydride shift, you get the carbocation there, and then you have heat, so now you can lose your beta hydrogen, and this has 3 hydrogens, this has 2, so you're going to lose the 2, so you can get your Yatsev's product, which is the more substituted alkene, which is more thermodynamically stable. So that's an E1, so that's not, you would never do an SN1 on that. but you still have to do your carbocation, your hydride shifts that you learned in the SN1. SN2, you're going to see SN2 in epoxide openings. So epoxide openings, and also what we call the Williamson ether synthesis. So you're going to see these, and you're also going to see these in alkynes, retrosynthetic analysis. So you're going to see those in those reactions. So I will go over, I will design a retrosynthetic scheme here as an example, and we will do an epoxide opening, and we'll do these three reactions in an example or two of that. So that's where you can see that you're going to need to know your SN2, backside attack, less hindered. And then that's also going to I'm going to try to kind of help you organize your thinking. Okay, so let's go with a retrosynthetic scheme. Okay, so retrosynthetic analysis. Let's do a compound such as this. And so in retrosynthetic analysis, you're going to be given a compound to start. So you might get something like this as your starting material. And you might get a compound like this, and this is the goal, to make this compound. So these are retrosynthetic arrows. And you need to recognize questions, how do I synthesize or make a diol? So what functional group do we need? Well, you know that you can make a diol from an alkene. And notice this is an anti-stereochemistry. So you need to know I make anti-diols from epoxides. Okay, so now we got to get to an epoxide. So here you would make this an epoxide. And make sure you have the right number of carbon. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. After every step, you should count your carbons. So you know that this is an anti-diol, so you can make this from acid and water. You could also make this from sodium hydroxide, step 1, and then treat it with some acid workup. And that would also make the anti-epoxide. Now, how did you make the epoxide? You do another retrosynthetic arrow, and you would have made it from an alkene. And what's your reagent? MCPBA. Okay, so that would make the epoxide. Now keep in mind, we have to get to this starting material and we have 3 carbons. So can you make an alkene from an alkyne? Yes. So you know you can do 1, 2, 3, 1, 2, 3, and then 4, 5, 4, 5, 1, 2, 3, 4, 5, 6. I think I added one more carbon. 1, 2, 3, 4, 5. So this is why we count our carbons, and we do it again, and we see that this carbon, carbon, carbon came from those 3 carbons, and then we have these 2 carbons here, and yes, you can make an alkene, and this is a transalkene. And so this would be from an alkyne, and that is sodium, metal, and liquid ammonia. So this is where you kind of have to remember your reagents and think like that. All right, so we're still not at our required starting material here. So now we have to see that we can break this bond here, and this comes from this, and then we have this here. So in order to make these 2 work, you need a leaving group. This is an SN2 reaction, and so the first thing you're going to do is you're going to treat that alkyne with sodium amide, and you're going to make the alkanide, and then you can do an SN2 with this alkyl halide here, and that would be step 2. Now, once you do your retrosynthetic analysis like that, you're required to go forward. So you do it like this, and then you say, okay, here we go. We have our compound here, and the first thing we're going to do is add sodium amide, which is a strong base. And then the second thing we're going to do is add our alkyl halide. And then you can draw your reaction there, your reaction product, CH2, CH3. And then the second thing you do here is you're going to reduce this sodium solid in a liquid ammonia. And then you can draw your trans. It's very important that you draw your hydrogens in so you can see that that's trans. Count your carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right, and then the next thing you do is you want to make the epoxide. So MCPBA. And that's going to make your epoxide. And we keep our stereochemistry. Notice that we have a trans here. 1, 2, 3, 4, 5. And then we're going to just add acid and water, and then you do your epoxide opening. And the important thing is just to show that this is anti. 1, 2, 3, 4, 5. And that is your product, your desired product. And you show that here. And that's how you do the retrosynthetic analysis. Okay, so another one we could do is we could do the Williamson ether synthesis. So if you have a compound like this, then you would want to break it here. And this is just showing you an example of an SN2 reaction where this would be a CH3 leaving group, and here you can make an alkoxide. And how do you make a sodium alkoxide? This is just an acid-base chemistry reaction where you can react it with a strong base. I guess the strong base that you're familiar with would be the sodium amide. So let's look at what that looks like. Don't put in your reaction arrows yet because this is an equilibrium. This is your base, plus, minus. This is your acid. This is your acidic proton. Your pKa for alcohols are 16 to 18. These electrons will come here. And then you get sodium alkoxide, which is what you need. And this is your conjugate base. And then you get the ammonia is taken. That's your conjugate acid. pKa is 35 for ammonia. You do have access to pKa charts. In a face-to-face class, you would not have that. You would have to memorize that. So 35 is going to go towards your products there by a long way. So this reaction here would just be, you would show your alcohol here. You could do step 1 with sodium amide, and then step 2 could be CH3Br, and that would give you your product here. And that would be an example of an SN2 reaction you might see. Okay, so I also wanted to tell you that a way to organize your thinking for these reactions. I think you need to think 3 ways to make an alcohol. So, and sometimes if you put numbers with it and you group them, you always have to group them with your functional group products, okay? So, from an alkene. So if we have this alkene here, or let's just do this alkene, and we have 3 ways to make an alcohol. So this is kind of just regrouping your POGL. If you add sulfuric acid and water to this alkene, it's always good to write your intermediate. You would get this carbocation intermediate, but then it would do a 1,2 hydride shift. So you would get a carbocation that looked like this, and then your water here could add as a nucleophile, and you would get a rearrangement Markovnikov. And this is a tertiary alcohol. So you look at that carbon, it's bonded to that OH, it's bonded to 3 carbons. That's a tertiary alcohol. Here, what if you added the mercury acetate? And then you did this in water, and then you treated it with sodium borohydride. Well, what's your intermediate? This is your intermediate. So you would have this carbon directs your nucleophile addition. There's your OH. And then this opens up some mercury acetate. You replace the mercury acetate with a hydride, and so you get a secondary alcohol. So you see this carbon bonded to the oxygen is bonded to 2 carbons. That's secondary alcohol. You get no rearrangement, and that's Markovnikov's. Here you could react this with BH3 in a THF solution. That's how you would have it in a bottle. And then you treat it with hydrogen peroxide and sodium hydroxide, and your intermediate is going to add hydrogen here and BH2 there. And then you just basically are going to replace your BH2 with OH. So then you get a primary alcohol. So you see that you have 3 different alcohols from the same alkene. But the key is when you're organizing all these reactions is to say, okay, I need to make an alcohol. And I can make that from an alkene. And now which reagents do I want? So it's another layer. Okay, another grouping would be making diols. So if you're going to make diols, you can make syn-diols or anti-diols. And you can do these from alkenes. So here, to make a syn-diol, then you would want potassium permanganate. And you want to do this in cold, mild conditions, because if you do it in strong conditions, harsh conditions, you're going to get cleavage. So you could just show your OH with both dashes. Some people are saying plus EN for the other enantiomer. Some people are drawing both enantiomers. I'm okay with any of these options. I just do one and just assume you know that's the other enantiomer, but I show that there is stereochemistry because this is syn. An anti would be, you'd have to do MCPBA, and you'd have to make your epoxide. And those epoxides are stereospecific, so I'd want to see some stereochemistry. And then you could show if you did this in acid and water, you're going to get protonation. And when you get protonation, then you have to attack your nucleophile from the more substituted. So this is going to give you often a different regiochemistry than what you would see with a basic solution. So if you did this with a basic solution, sodium hydroxide, and let's erase these arrows because we really only want 2 or 3 electron flow arrows towards a product. So here this is going to come from the least substituted side and do an epoxide opening. And you're going to see, you probably have to treat this with a little bit of acid afterwards. Okay, but so that shows you an anti. And you're not going to really see the difference here, but if you had, let's say, sodium methoxide, then, and then you treat it with a little bit of acid, this situation, let's erase these electron flow arrows again. This situation, you're going to see that the regiochemistry is going to make a difference in your product because you would have the OCH3 adding to this carbon as opposed to the other substituted carbon. So those are another way to group your reagents. The last one here, actually we'll do two more, an ozonolysis. So ozonolysis. So ozonolysis will show of an alkene versus alkyne. So now you've got alkyne reactions, and so if you do ozonolysis, we're doing ozone, and then we're going to treat it with DMS. Then this is a mild cleavage that it will give you an aldehyde. So, and then you also get formaldehyde. So if I were you, I'd be grouping these reactions together. And then what's the difference? Here, for an alkyne, you're going to get a carboxylic acid. And then this carbon will be also a carboxylic acid. But over here you have a hydrogen and you keep the hydrogen. Now, what if you did permanganate, KMNO4? Now, if you did this harsh, so we do this maybe heat and some base, so some harsh conditions where you can cleave this, you're going to get the carboxylic acid plus the terminal is going to go to carbon dioxide. Okay, carbon dioxide. This terminal will go all the way to carbon dioxide. Here, if you did permanganate and heat, then you're going to get the carboxylic acid, just the same here, but this terminal will go to carbon dioxide, which is the same thing as CO2. So kind of grouping these together should help you. Okay, and the last grouping together, let's just look at these reagents here. So we've got mercury sulfate and sulfuric acid. H2SO4, or we have the, this one is SiA2 borane, and then you treat that with hydrogen peroxide in a basic solution. Now what happens here for an alkyne is if you do the first one, you're going to get a ketone. 1, 2, 3, 4. 1, 2, 3, 4. The second one, you're going to get an aldehyde. So count your carbons here. And so then you can review those mechanisms. So what is the intermediate in this reaction? And on your all's open response, I did put intermediates because I think if you draw the intermediates, you're going to get the reaction correct. Okay, this is HBr. Now, if you did just HBr, with just HBr, you would get, okay, that's an acid, you got an alkene, you're going to get protonation. This was one of your Pogel problems. And you get the carbocation because you want to follow Markovnikov's rule. And then the bromide will come in and add in step 2. And so you get Markovnikov's, the more substituted product. But here we have a peroxide. And so when we have HBr and a peroxide, you get this peroxide initiation with HBr, and this will take, we're going to have fishhook arrows because we have free radicals. So this is going to make some methanol, and then you're going to get this bromine radical. So now for propagation, so we'll go down here for P1, propagation with your Br radical, the bromine radical is going to add. We got fishhook arrows here. 2 electrons go there, and now you get a free radical intermediate. The bromine adds. This becomes a radical, the more stable radical, and the bromine adds first. And when the bromine adds, just like the hydrogen adds first, this is our more stable radical, free radical. So the peroxide here, the alkoxy peroxide, will change the mechanism. And so P2, it would be this reacting with another HBr, and you get the fishhook arrows here, and now you get your product where the hydrogen has added second and the bromine added first. So you can see your product's different here than it is in this first reaction. And this would be the anti-Markovnikov product. But it's only asking you for the intermediate. So if you went through your propagation steps, you would have drawn this intermediate, and you could see your options are a carbocation. It's not a carbocation. And then you see that the bromine has to add to give you that free radical. Okay, reaction intermediate for this one. Okay, so our reaction intermediate again. And this is an alkene, and you're adding the BH3, and then you're treating it second with hydrogen peroxide and sodium hydroxide. Now, with BH3, you could do H-BH2, and basically your BH2 is going to add to the least substituted carbon, and then the hydrogen is going to add to the more substituted carbon. So, and it's going to be on the same side, so you want to make sure that these are both dashes or both wedges. Your options were this compound here, or the BH2 adding to the more substituted. You do not make a three-membered ring, and you do need to add your BH2 because it asks for an intermediate. Okay, question number 4 was about a reagent. So here you're picking your reagent. We have an alkene, and we're making an alcohol. And so this is one of those 3 ways to make an alcohol. So if you go back to your 3 ways to make an alcohol from an alkene, you'll say that this one is our anti-Markovnikov. And this is kind of like what you basically had to do in your POGIL exercises. So you should know that step 1, BH3, and the THF is stabilizing. And then this is hydrogen peroxide in sodium hydroxide solution. And what is your intermediate? I always like to do my intermediate. Hydrogen would add here, and the BH2 would add here. And then step 2, the hydrogen peroxide would replace the BH2 with an OH to give you your anti-mark. So you can see that your other options were the Markovnikov with the mercury acetate, also the Markovnikov with the sulfuric acid, and then the bromine and water would make a bromohydrin, bromohydrin. Okay, and the last question was product. So if you produce your product here, you have an alkene. First step, you add MCPBA, and then your second step, you're adding acid and methanol. Okay, so your first step, so you always want to go with your first step when you have stepwise, and you can show the stereochemistry here. So you make an epoxide. And then your second step, you protonate it. Okay, so we're adding acid, so that means the epoxide gets protonated. And this is going to make the mechanism different because now you have a three-membered ring that is charged. This is an oxonium ion. So that means the nucleophile is going to be directed to the more substituted delta positive. So your nucleophile is methanol, and methanol is going to come and open that ring. So you have an epoxide opening. This was also one of your POGIL exercises for this week. So the alcohol will add to, and you'll get, the CH3 will add here, and then the important thing is that the addition of your nucleophile is anti to your alcohol. So now when I look at your products, I see that we have that option. Your other options that were not okay were the OH being on the tertiary. So this alcohol here is bonded to 2 carbons. So that carbon's bonded, that's a secondary alcohol. This carbon is bonded to 3 carbons. That's a tertiary alcohol. The regiochemistry is incorrect here, okay, because your methanol, your methoxide, methanol nucleophile opens from the more substituted. The epoxide, one of your answers was this, but that's not correct because that's only from step 1. You've got to go all the way to step 2. And then the other option you had was an anti-diol, and that would be okay if your nucleophile had been water. So those are the details you've got to pay attention to on these predicting the reagents. And that goes over your 5 multiple choice questions from quiz 6. So I hope this was helpful.